start off looking at chapter 5, because this is going to be on exponential functions. And what we'll do first is just compare the kind of graphs we've been looking at, which are like polynomials, rational functions, things like that, with an exponential. Okay, so I'm going to graph x squared, and then I'm going to graph 2 to the x. So let's put in x squared and 2 to the x. Okay, and I'm going to do zoom 6. Now you'll notice x squared does go negative infinity to infinity on the domain. So does 2 to the x. So that part's the same. They each have the same domain. And it's a little hard to see in that window. But what do you think is going to happen as we continue to the right? If you compare the red graph and the blue graph as we continue to the right, what do you think is going to start to happen? Travis, any guess?
You go up exponentially.
Okay, which one is going to go up faster?
Red one?
Yeah, the red one is going to start to go up faster. If we set the y-max higher, then we'll definitely start to see that. Okay, so let's try putting it at 60. Okay, there's not much to see on the left. That's just going to stay flat pretty much the whole time. But then if you look at the red one, it definitely starts to curve up faster. Okay. Okay, it does look like there might be a period where the red one does go underneath the blue one. So squaring gives you a bigger result for a little bit of time, but eventually exponential will always be squaring, okay, in the long run. Right? It gets bigger, faster. The other way we can see that is if we go to the table. Right, if we plug in a number like 0, the red one is a little bit higher. If we plug in a number like 5, okay, the red one is starting to get higher. And then by the time we get out to 10, the red one is way higher. Okay, much, much higher. All right. Now, if we start to go to the left, you'll notice that the red one starts to level off. Why is that? Why does the red one start to kind of level off and it looks like it's having an asymptote to the x-axis? Somebody explain why that's happening in this one. Yeah?
If it's a negative exponent, that would be a fraction.
Right. Okay, if you've got a negative exponent, let's say x is negative 5. Well, if we rewrite that so we don't have a negative exponent, it would be 1 over 2 to the 5th. So what we start to get here is a denominator that's going to get bigger and bigger and bigger. Well, if your denominator is going to be getting bigger and bigger, the further to the left you go, what happens to your entire fraction? Yeah?
Wouldn't it just get closer and closer to 0?
Right, it approaches 0. Exactly. So the further to the left you go, the bigger negative number you get, the smaller that the result becomes because it's in the denominator. Yep, exactly. Right, but that's what a standard exponential function always looks like. Okay, if you don't shift it, stretch it, reflect it, it always has a positive slope. And as you head to the left, it has an asymptote at the x-axis. Okay, so in each case, we do have a base and we have an exponent. When we have like a polynomial kind of function, the base is a variable and the exponent is an integer. When we have an exponential function, the variable becomes the exponent, or the variable is in the exponent. That's what makes it exponential. How about if I graph this? Do you think that would be considered an exponential function? It's got a base that's a number, and it's got a variable that's an exponent, just like the one I just did. No? How come?
Because when you multiply 1 by 1, it's always going to come out to 1.
Right. So in this case, when you have a base of 1, that's not considered exponential because that would just be the same as graphing a horizontal line at 1. Okay, and we'll clarify that in a minute. We're going to write that down. Okay, so this is the kind of thing we've been working with a lot this year. Okay, polynomials. Polynomial is when your variable is in the base and the exponent is a non-negative integer. Okay, like quadratics, cubics, quartics, those are all polynomials. But when we make it so that the variable is an exponent, and this is what we just said, the base is a positive real number, but not 1, that's an exponential function. Okay, so for exponential, you've got to have an exponent, that's a variable, and you have to have a base that's not 1. And it has to be positive. It can be a decimal, can be a fraction, but it does have to be positive. Let's look at what would happen if it was negative. Okay, let's think about that. So if we had y equals, let's say, -2 to the x. And we start to make a table for that, like we were going to try to graph it. What if x is 0? What's -2 to the 0 power? Yep, 1. Okay, so there's 1 point, -0, 1. How about if x was 1? What's -2 to the first power? Definitely.
Sorry. If x equals 1, then y would equal -2.
Yep, -2. All right, so we just got a positive value for y, we got a negative value. Now, how about if x was 2? Jane, what would y be in that case? 4. And then if x is 3, we get -8. So as we start to graph that, it's like the y value is oscillating between negatives and positives. So that would be kind of strange. And then let's just say we made x a half. Raising to the 1/2 power, what's that the same as doing? Yeah?
Square root.
Square rooting. If we take the square root of -2, we get I square root 2. This graph is all over the place, right? Sometimes we get negative values for y, sometimes we get positives, sometimes we get imaginaries. You can't really graph something like that. And if you try to, you won't even get a picture. It's just not something you can graph. Okay. But if we go to our table, we can check the values we did. We type in 1, 2, 3, 3. And then if you do 0.5, 0.5, it doesn't even tell me what it is, but actually, even when you put the calculator in imaginary mode, it still doesn't tell you what it is. It says error. I mean, technically, it is I square root 2, but the calculator is not able to figure that one out. All right, so we're not even going to consider when the base is a negative, only when the base is a positive real number, but not 1. Okay, so let's go back to our graph, and let's just look at the exponential. But let me get rid of that negative. What did I say earlier the domain is for that? About Marin, what's the domain for that? Right, it's all real numbers. You can, when you're dealing with an exponential function, you can have any number you want for the exponent. Okay? Positives, negatives, zeros, fractions, decimals. Anything works for the exponent. Exponent. What about the range here? Just that one. You know, yes, we could shift it, we can stretch it, flip it, but just looking at that picture, what does it look like the range is? About Ethan?
Like all positive.
All positive? Yep, so how would you write that, let's say like as an inequality? Y is,
Greater than or equal to 0.
yeah, so greater than or equal to 0. That's a little different than what you said. Is it all positive numbers, or is it all numbers greater than or equal to 0?
Greater than or equal to 0.
Okay. Anyone have any thoughts on that? Greater than, he said greater than or equal to 0. Yep.
It's just greater than 0.
It's just greater than 0, right? Because this is, if you think about it again as a fraction with a negative exponent, I don't care how big you make that number, 1 divided by anything is never going to be 0. Okay, so you will never reach 0. The only way you can is if you took this function and you shifted it. Then you could hit 0. All right. But there's your domain. And the range, actually, I guess I didn't write the range. I'll write the range for this one. Okay. This never changes. Doesn't matter how you transform an exponential function. Shift it, stretch it, flip it. It's always going to be negative infinity to infinity. But the range can change. That depends on any transformations that you've done. This is just explaining again, the base is any positive real number except the number 1. Okay, so those are all examples of exponential functions. The base can be irrational, that's fine. Irrational can be a positive, that's definitely a positive number that's not 1. 3.14 keeps going. These are all examples of functions that are not exponential. What's this first one? F of x. How would you describe what that one is? Yep.
Cubic.
Yeah, that's a cubic polynomial. Yep, that's not exponential. Okay. This next one, that's a quartic polynomial. And then the last one, that one doesn't really fit nicely into a category. It's kind of a combination of a rational function, because it's a fraction. But in a rational function, you're supposed to have a polynomial in the top and the bottom, and that top is not. Top is a radical. So it's kind of a mixture. But it's definitely not exponential. Right. Let's look at the difference between 2 to the x and 3 to the x. Okay, so we've already got 2 to the x. I don't need parentheses around the 2. I think I had a negative. That's why they're still there. It won't hurt anything, but you don't need them. Okay, so there's 2 to the x, and the red one is 3 to the x. What do you notice happens with 3 to the x? Oh, Jackson, what do you think? What happens with 3 to the x?
It starts getting higher, but it never gets higher than the red line.
Can you just say that again for me?
So it starts getting like higher, but it never gets. But it doesn't get higher than the red line.
What does it get higher than the blue one?
Oh yeah, Oh, sorry, I got them mixed up. Never gets lower than the blue line. I mean,
Okay, how about in terms of this, let's talk about like the slope as x approaches infinity. What do you notice about the slope?
It starts to like look undefined, like it starts getting higher.
Well, they both do. I would say they both are getting steeper. But how about if we compare the two to each other? Yep.
One increases faster.
Right. The red one has a faster rate of change than the blue one. Okay? It is increasing faster, especially when x starts to approach infinity. Yeah, the blue one is steep too, but it's not as steep as the red one. Right? So the bigger you make that base, the faster it starts to increase. That slope starts to get steeper and steeper. Now we could look at what's happening in here. As you head to the left on both of these, they are both getting flatter. The slope is approaching 0 as you head to the left. And it's increasing as you head to the right. Okay, so it's a pretty typical exponential. Now, if we ever raise something to a negative exponent, that's going to make it complicated to analyze. Right? So like if you had these two graphs and you wanted to compare them, you really can't the way they are. When you compare two graphs, you want the exponents to be positives. Okay? This negative is going to cause a reflection. So if we can think of it without the negative, it's going to be a lot easier. So let's see if we can figure out a way to get rid of a negative exponent. Kind of mentioned this earlier, but a to the negative 1. How could you write that without a negative exponent? A to the negative 1. Yeah.
1 over
Yeah, that means 1 over a. Okay, so it just when you raise something to the negative 1, it just means reciprocal. So now, let's see if we can use that idea to simplify this. We have a to the negative x, and the goal is to get rid of that negative in front of the x. What number is in front of the x, even though it's not written there?
1.
Yeah, or in this case, it's like having a negative 1. So you could think of it as, let me just write it in like that. It's a to the negative 1 times x. Anybody remember there is a rule for when exponents are multiplied together like that? When does that happen? Yeah?
Usually it happens when, say you're multiplying two numbers and they have the same base, and I think that's when you can multiply the exponents together. I don't know the name exactly.
So when you're multiplying two things with the same base like this, that's when you add the exponents.
Oh, then it's probably one is in parentheses and another exponent is like outside.
Yeah, when you have a power raised to another power, like x to the 3rd to the 5th, that's x to the 15th. Okay? So the only way that you could end up multiplying a negative 1 times an x is if you had a power raised to another power, a to the negative 1 to the x. Because if you simplify that, it would be negative 1 times x, or negative x. And the reason I did that is because now we have that, a to the negative 1, and we have a way to fix that using what's up above. So basically, anytime that you see a negative in the exponent, you can take the base and flip it, and that will get rid of the negative. So like if I had something like 3 to the negative x, and I was trying to describe the transformations. Well, one thing they might ask me to describe is it exponential growth or decay? You might look at that and think, once we learn a little more about it, that it's growth, because the base is a number bigger than 1. But because it's a negative exponent, it's not really a number bigger than 1. That is really that, which is exponential decay, not growth. So the negative exponent can kind of hide some things that we want to be able to see. So we usually try to get rid of a negative exponent using this rule right here. Okay, so let's compare these two graphs. We're going to fix them so that we don't have any negative exponents. We'll graph them, and then we'll compare the domains and the ranges of each. Okay, so f of x is fine. Okay, that's written in what we would call like standard form. Easy to compare to other functions that have a base of 2. This one, not so much. How could we rewrite that so it doesn't have a negative exponent? Yeah.
1/2 to the x.
Right. That's the same as 1/2 to the x. And by writing it that way, it's going to make it very clear that this is a decay function, not a growth function. All right, so let's graph, and then let's look at the domain and range of each. Okay, so I've already got 2 to the x, and I'm going to do 0.5 to the x, same as 1/2. Okay, I'm going to do zoom 6 just to reset everything. And remember that negative inside the function. When you have a negative inside, that's a horizontal reflection. So these two graphs should look like horizontal reflections of each other. Okay, let's start with the domain of each. What's the domain of f of x, which is the blue one? How about, Dario, what's the domain of f of x?
Y is greater than 0.
All
real numbers.
Yeah, all real numbers. And what's the domain of g of x?
All real numbers.
It's also all real numbers. Right? No matter what kind of exponential function you have, transforming it will never change the domain. That's what I put down right there. Domain never changes. Okay, so we've got negative infinity to infinity. And same thing there. Okay, how about the range? Layla, what's the range of f of x? Yep, y is greater than 0. And how about g of x? So you think the red one is every number that's below the below the x-axis? Yeah. Okay, the domain and the range for both of these are the same. They look different, but they do have the same domain and ranges. And if we want to say y is greater than 0, how do we do that in set or interval notation? Just because we already did the domain that way, so let's stick with that for now.
Parenthesis 0, comma, infinity.
Yep. Okay. So same domain, same range. So that's looking at it for a specific value of a. Okay, we looked at it when a was 2. It doesn't really matter if a was 2, 3, or 17. Okay? We're still going to have the same looking graph in every case. It might be a little steeper or a little less steep, but it's going to have the same basic behavior. All right, so let's see if we can figure these out. So the first one is saying as x approaches infinity, what happens to f of x? Okay. F of x, if you want a more concrete example, it's like the graph in blue. Okay. Whether it's 2 to the x or 12 to the x, the answer to this question won't change. So what happens to the y value in the blue graph as x approaches infinity? Yeah.
Y approaches infinity.
Y also approaches infinity. Yep. And again, still focusing on f of x, which is a growth function. As x approaches negative infinity, what does y approach in that case? Raj? 0. Yep. Approaches 0. Okay. Now we're going to look at g of x, which is more of what we call a decay kind of function. Okay. So that would be the red one. Well, everything is going to reverse. So in a decay function, as x approaches infinity, the y value approaches 0. And as x approaches negative infinity, in the red graph, the y value approaches infinity. Okay, so any question on the behavior of, again, what we're going to refer to as a growth function and what we'll refer to as a decay function in a few minutes. Now, that's assuming that you do not do anything else to it. Okay? In this case, all we're doing is changing the base. We're not stretching, we're not shifting, we're not reflecting, none of that yet. Okay? So the big difference between those two graphs that we just did, one that looked like growth and the other one that looked like decay, was whether the base was greater than 1 or between 0 and 1. All exponential functions that have a base bigger than 1, if you don't do any transformations, will look very similar. All exponential functions that have a base between 0 and 1 will also look similar. Okay? They're going to be decay functions. Okay, and I don't think... well, we're not going to go through the reasoning on that, but exponential growth and decay functions are reflections of each other over the y-axis. Okay. So I would just write that part down. Growth and decay functions are reflections of each other over the y-axis. And that's assuming you're comparing two graphs that have the same a value, like 3 to the x and 1/3 to the x, or 10 to the x and 1/10 to the x. Okay, but that's all you have to write down, it's just the reflection piece. All right, so transformations are exactly the same. I'll put the diagram up, we'll go through it verbally, but I am not going to write down every step because we've done it so many times. All right, so exponentials. So you'd have a base. Again, the base could be a 2 or 3. The base doesn't really matter. But it would look something like this. That would be considered the parent function. Right? There's no transformations to it. It's just an exponential with a base of 2. All right, so we could have that. That would all be considered inside the exponent. Okay, that's inside the function. And on the outside, we could have something like that and something like that. Okay, so we'll go through what each letter does. Again, if you're not sure, I would write it down. But let's start with the A. A is addition or subtraction on the inside of the function. That inside in this case means in the exponent. What's A going to do? Yep.
Cause reflection?
No, A won't do any kind of reflection. There are going to be reflections, but it just won't be with A. Yep.
Horizontal shift.
That A is a horizontal shift. Horizontal shift. Anytime you are adding or subtracting inside the function, inside the exponent in this case, horizontal shift. Positive will shift it to the left and negative to the right. Yep. How about B? Still inside, but now it's multiplication. What kind of transformation is B? Yep.
Horizontal stretch.
Yep, B is a horizontal stretch. If B was 2, how would you describe the horizontal stretch? If B was 2, yep.
It would be like a stretch by a factor of 2. I know you have to replace the word stretch with something else.
You would say horizontal stretch by a factor of, but how much? What would it be by a factor of? Wouldn't be 2. Yep.
Would be a half.
Be a half. Remember, B is always backwards. The bigger you make B, the more squished the graph is going to get. Right? So like if I do 2 to the x and I do 2 to the 5x, right, let's look at the difference. So there's 2 to the x, and here's 2 to the 5x. So what happened is if I take the graph in blue and I start to squish it horizontally, if it lets me do it. Okay, I put in an exponent of 5. That means I squish the graph 5 times as much. So let's see if I can. I think that's about where the window was. Yeah, pretty good. Let me squish it 5 times as much. So if I cut it in half, it would be here. Half again would be a quarter of it. Let me squish it down to like right there, if it lets me. Yep, it'll let me. So I'm going to take this. I'm squishing it by a factor of 5, and now I want you to compare it to the red one. There you go. That's a horizontal compression by a factor of 5. So usually we say stretch by 1/5. Does that make sense? Okay. So we've got A and B. What if B is a negative number? What does that cause the graph to do? B is negative, yeah?
Would it expand instead of compress?
No. So remember B alone causes whether it's a stretch or compression. So if B was like 1/3, that's what would cause it to stretch. It would stretch 3 times as much. But a negative on the B causes something else. Reflection over which axis? So remember, B is horizontal. So when you reflect something horizontally, y-axis. Yeah. Okay, so B is a horizontal reflection over the y-axis if it is a negative number. Okay. What about C? What kind of transformation would C be? Yeah.
Vertical stretch.
Yeah, vertical stretch. And this one, there's nothing backwards about it. The bigger you make C, the bigger stretch you get. If C is 5, it's a vertical stretch by 5. If C is 1/2, it's a vertical stretch by 1/2. What about if C is negative? What does that cause the graph to do? Yep.
The reflection of the x.
Right. If C is negative, you're going to get a reflection like that. A vertical reflection, because C is vertical. That's over the x-axis. And the last transformation, plus or minus D, what's that going to do? Yep.
The vertical shift.
That's your vertical shift. And positive would move it which way? Yes. What kind of shift is it again?
It's separated.
Vertical, yeah.
So, is it still opposite?
No.
Oh, so
Nope. Up. Yep. If it's positive, it's up. If it's negative, it's down. Okay. So there's the 6 different kinds of transformations that you can have. So let's look at this one. First of all, when you are doing transformations, you would always compare things with the same base. So you'd never compare like 3 to the x to 2 to the x. Those are different. You can compare 2 to the x to 2 to the x. Yeah.
I have a question for the last one. What if B and C are negative? Like,
What if they're both negative?
no, not negative. Like, does it still reflect over the same axis?
No. Unless B and C are negative, there's no reflection.
No flexion.
No. So basically, an exponential function is either going to look like this, or it could look like that if you reflect it horizontally. Or if you reflect it vertically, you could get something that looks like that, or you could get something that curves the other way. Those are the 4 different looks that an exponential function can have. All right, so let's describe the transformations. Good step is always to figure out how many you have. How many transformations would it take to turn f of x into g of x? Marcel? 3. Yep. So we're going to do 3 transformations. Remember, when you list the order, it is like a PEMDAS kind of situation. You have to put them in the right order, but you always follow the chart that I gave you. Start with A, so that would be your horizontal shift. B would be your horizontal stretch, then your horizontal reflection. Then C would be your vertical stretch. Could also be a vertical reflection. And D would be a vertical shift. That's the order that you need to follow. If you're missing any that are in the order that I just said, then you skip it. Okay. So what number would we focus on first in this case to get our first transformation? The positive 1. Yep. What's the +1 in the exponent going to do? Yep, Vanessa?
It's going to shift it left.
It's going to shift it left 1 unit. Good. All right. So we dealt with that. What number are we going to focus on next? Jackson?
Positive 2.
Positive 2. And what's that going to do?
Vertical stretch by factor of 2.
Yep. Vertical stretch by a factor of 2. So that means if you had a graph that looked like that, and there's your limits to your box, you're going to make that box twice as tall. So if that was the box, vertical stretch by a factor of 2 is going to bring it up to there. Without changing the width. Okay? You just make it twice as tall. So it would probably look something. That's not good. That's pretty good. Okay, about like that. Okay. And how about the -5 on the end? What's the -5 going to do? That?
Would it be a vertical shift downwards?
Yep. So we're going to shift down 5. Any questions on describing the transformations or what the A, the B, the C, and the D do? Okay, so by now, that's like the 4th or 5th time we've looked at it. We did it with rationals, we did it with radicals, we did it with, I think we did it with quadratics. So we really, should start getting pretty comfortable with what the A, B, C, and D do, and that the A and the B are always backwards, and the C and the D are not. Okay, we will look at it one more time when we do logarithms. And that'll be the last time we do transformations in the algebra part. And then the next time we see them, it'll be with trig, okay, when we do graphs of trig functions. All right, so when you first look at these two graphs, f of x and g of x, they look different. Okay, so we want to prove that these two graphs are the same. Okay, why would you have to prove two graphs are the same? Well, when we start to do a word problem, and you come up with an exponential equation to model the word problem, you might get an answer that's equivalent to my answer, but your answer looks different. So you have to know how to take an exponential equation or expression and manipulate it to look like something else. All right. You can pick either one, whichever equation you think is going to be easier, but the goal is to pick one of them and work with it until you change it into the other one. I'm going to try to work with f of x. Anybody see something we could start to do there to at least make f of x look a little bit more similar to g of x? Yeah.
You could move the negative to rest to
Yeah, let's at least fix the order in the exponent so that everything is in the right order. G of x has the letter first, and it has the number second. That's the way I describe to you the transformations. I always put the letter first, and then I put the constant last in the exponent. Okay, so let's do that. So we have 2 to the negative 2x plus 3. Okay. Anybody see what we could do next to start to make at least this part of the exponent look a little bit more like g of x? Why is the part with x in the first function and the part with x in the second function, why aren't they the same right now? What's preventing them from being the same? Yep.
Negative 2 in front of x.
We have a negative 2 in front of it. What could we do? We can't just cancel out that negative 2, but we can do something with it. Yep. So not divide by it. But yep.
Can we factor?
We can factor it out. Okay, so let's factor out that negative 2, so that way we have just an x left. And the other thing is, it's also a negative. So we probably should factor out the negative with the 2. So let's do that. So if I factor a negative 2 out from this exponent, what would I be left with inside my parentheses? Yep.
X minus 1.5.
Great. I'd be left with x minus 1.5. Because if we distribute it back out, we'd get back what we just had. Now, if you look at what's happening here, we have negative 2 times, and then we have something in parentheses. We're multiplying two things together inside an exponent. When does that happen? We talked about that earlier. When would you end up with multiplication like that inside of an exponent? If you originally had something like what? Yeah.
You put like the 2 to the negative 2 in parentheses.
Like that?
And then you raise it to the power of x minus 1.5.
Yeah. Okay. If you're multiplying two things together inside the exponent, that would have come from a power raised to another power. So this came from what's below it. And now, there's one more thing I can do with that. I have a numerical expression in my base, 2 to the negative 2. Well, what does 2 to the negative 2 mean? Raj? It means 1/4. That's 1 over 2 squared, which is 1/4, which is the decimal 0.25. So this is 1/4 x to the minus 1.5, which is the same as 0.25 as a decimal. There you go. So we manipulated it algebraically to show that f of x and g of x are exactly the same. Okay, if we were going to try to describe the transformations of this, it's probably easier to have it this way. Usually we like to have the letter first, so then we can see that it's a shift to the right 1.5 units. That's all that's happening. If you describe it with this base. If you want to try to describe it with this, you can, but you'd have to describe more transformations. You actually have to describe 3 transformations if you want to think of it as having a base of 2. You'd have to say that it's been shifted to the to the left 3 units, vertically stretched by a factor of 2, and then reflected horizontally. So those 2 sets of transformations I just described will result in exactly the same picture. But g of x is much shorter to describe than f of x. It's more efficient. All right. So let's take a look at this graph. Okay. Something's going to happen here that we're going to talk about more later in the week. But for now, I just want to look at it. And I kind of want to think of what's going to happen as x gets bigger and bigger and bigger. What happens to this? Just the part I circled in purple. As x gets bigger and bigger and bigger. Yep.
Approach 0.
This approaches 0. Okay. So as x gets bigger, that approaches 0. So what happens to this thing that I just circled in blue? As x gets bigger and bigger and bigger, what's circled in blue will approach what? Yeah?
1.
This will approach 1. So we have a number that's approaching 1 being raised to an infinitely large power. So what's going to happen there? It's approaching 1, but it's never reaching 1. If it was 1, then 1 to any power is 1. But it's not 1. It's a little above 1. And you might think, well, as you get bigger and bigger and bigger, it's just barely above 1, right? It's like 1.0000001. It's not that much above 1. But it's being raised to an infinitely large power. So what's going to happen? Well, let's graph and let's see. So we have 1 plus 1 over x raised to the x. Well, we definitely have a discontinuity at 0, because if you try to plug in 0, you'd be dividing by 0. And if you go to your table and you plug in a number like 0.01, you do get a value, so you can check a value very close to it, but it's not dropping down forever. Okay? Like if you do 0.00001, it's not going to negative infinity. On the other side, negative 0.01, let's see. Oh, yeah, we got to be careful with negative exponents because then it starts to get weird if we use decimals. So let's just look at that graph. Did anybody notice something that that graph might have? We talked about in the last chapter. If you look at the end behavior, what does it look like is happening? Dario?
Does that have a slant asymptote?
So you're on the right track. This one does not have a slant asymptote, though. But we're on the right track. Any other thoughts? Raj?
Horizontal asymptote.
It does. It has a horizontal asymptote. And let me type this in. Let me press second divided by. Just put in E. Has anybody heard of E before? E is a constant. It's like pi. It's just a number. And when I hit graph, it looks like that horizontal asymptote in that graph is very close to a special number, which we call E. Okay? From the graph, you can see it's a little bit less than 3. That's the horizontal asymptote. And if you press table and you start putting in bigger and bigger numbers, you're going to notice you're getting close to this number that's about 2.718. It doesn't end there. Okay, it goes on forever. But we're starting to get E. E is the number that's in red. Okay, right there. As the blue graph heads to infinity, the value of it approaches the red graph. E is a special number called Euler's number, spelled E-U-L-E-R. But it's pronounced Euler because it's German. And when we start talking a little bit more about logarithms, we're going to talk more about E. Okay, but I bring it up here because it's kind of this isn't what we usually look at for exponential functions, but it does have an exponent that's a variable. And in calculus, you could prove why this has an asymptote at the number 2.71828, and it keeps repeating. Okay, that's not something we would prove in this class, more of just an interesting fact to notice. We just get this asymptote at this very special number. Okay, but that's all I'm going to say about E for today, but I will write it down. It's Euler's number. And we'll talk more about logarithms probably tomorrow. All right, so the last thing we're going to do is look at exponential growth and exponential decay. Okay, and we're going to see if we can come up with some formulas to predict growth and decay. So we're going to start out with a population problem where the population of the town is increasing at a certain rate. Whenever something increases at a percentage, that is exponential. So like if you work at a job and you got a 2% raise every year, if that continued to infinity, that would be an exponential growth. You're getting 2% more money each year. Compared to if you said you get $500 more each year, that's different. That's linear growth. That would just be a slant. All right, so this particular problem, at the beginning of our experiment, the population is P. That's the initial value of the population in the town. All right. Now, let's say that the population of this town was going to go up by 10%. how can you figure out, and I said to you, okay, tell me how many new people are going to be in the town this year. Okay. How do you figure out 10% of something? Yeah?
P times 0.1.
Yeah, you do P times 0.1. So if you had 100 people in the town, and I said to you, we're going to have 10% more people this year, you could multiply it by 0.1. That's how many new people are going to be in the town, 10 people. How would you figure out the total population of the town now? That's just how many new people there are. Assume nobody dies, nobody moves out. Yeah?
Add the 10% to the original population.
Right. If you take the original population, so this is the original amount. This part right here is the increase. It's your population times your percent. 100 plus 10 gives you the new population. All I've done with the expression on the right, and you'll see why in a minute, is I factored out the P. Okay, so for year 1, this was your original population. This was the amount of increase. Now, let's look at year 2. What is the starting population for year 2? It's not P anymore. P was the starting population, like at the beginning. What's the new kind of starting value that we're going to use for the population at the beginning of year 2? Yeah?
Use the P, the parentheses as well.
Right. This was the new population at the end of year 1. That's going to be the population I start with at the beginning of year 2. That's now the original amount. And let's say I said that's going to increase by 10% again. What would I do to find out how many new people are going to be in the town if that amount is going to go up by 10%? Yeah.
Would you put the parentheses to the power of
So no, not a power. Think about how we did it for year 1. We're going to do it kind of the same way for year 2. Yep. Okay, what would you add to that? And how would you find like 10% of this? How do you find 10% of anything? Yeah?
Multiply by 0.1.
Multiply by 0.1 or multiply by your rate. So what do you think I'm going to have right here if I want to find R percent, whatever R is? It's not 10, it could be any number, but I want to find a certain percentage of this. Yep.
Plus that multiplied by R.
Plus that multiplied by R. Exactly. So it's always the amount you started with plus the amount you started with times R. That's the original amount. There's the increase. And now, what can I factor out of each of those? What do they each have in common? Yeah. Right, they each have a P times 1 plus R. And if you factor that out of here, you'd be left with a 1. If you factor that out of here, you'd be left with just the R. There's the 1. There's the R. So I factored P times 1 plus R out of both boxes. And what does that simplify to? P times 1 plus R times 1 plus R. Like if we could just shorten this a little bit, how could we write that in a shorter way? Yeah.
P 1 plus R to the power 2.
P times 1 plus r to the power of 2. So we had P times 1 plus r to the power of 1. P times 1 plus r to the power of 2. What do you think my population would be for year 3? Yeah?
3 times P plus times 1 plus R to the power of 3.
P times 1 plus r to the power of 3. Exactly. So how about if I wanted to figure out the population after t years? What do you think the formula would be for the population of this town after t years have gone by? Yep,
P times 1 plus r to the power of t.
exactly. It's p times 1 plus r to the power of t. And you could keep going with this pattern. You could do it for cubed, and you could see the pattern. I just did it for the first two. But that is the exponential growth formula when you have an initial amount increasing over time. So the values you have to plug in are the initial amount. Could be an amount of people, could be an amount of anything. R is the rate of increase. Make sure you change it to a decimal. So if R was 10%, you'd plug in 0.1. And T, that's the time that has gone by. It's usually like the number of years or something like that. Now, if we change one thing in that formula, we can make it, instead of an exponential growth formula, we can make it an exponential decay formula. What do you think would change to make that into a decay formula? Yeah? Yeah, we would change the plus r to a minus r. So if you had a population in a town that was decreasing at 10% every year, you'd use this formula. All right, so let's try an example. It says that we have a town that has a population of 50,000 people, increasing at 2.5% per year. They want us to graph it and basically find when the population doubles. So we're figuring out how long it takes the population to get to 100,000 people. So we're going to write down our population as a function of time. What's the initial amount of people in this problem? Yeah.
50,000.
Yep, starting with 50,000 people times 1 plus my growth rate. My growth rate is 2.5%. But if you change that to a decimal and add 1 to it, what would go inside my parentheses? Yeah.
1.025.
1.025 to the t. There you go. So there's your population. And now they want us to figure out when that reaches 100,000. Well, what's the smallest that the population will ever be in this town? Yeah.
2,000.
Right. It can't go below 50,000, so there's no reason to look below that. So we're starting at 50,000 people. And we want to know when we get to 100,000, so I'm going to go a little above it. X is the amount of years that have gone by. Let's assume this happens within 40 years. If that's not enough time, we'll have to adjust it. What else would I need to put into my y equals screen to be able to solve this graphically? Yeah?
100,000.
Right, I need a mark at 100,000. Okay, so here's the population. And you'll start to see it. It is a curve. It's not a straight line. But it's not a huge percentage. It's 2.5, so it's not as much of a curve as we're used to seeing. And then we just have to calculate the intersect. There you go. So it's going to take about 28.07 years for the population to double. Any question on that? When you're graphing, as always, be careful about including negatives. A lot of times negatives don't make sense in a word problem. Okay. So the last thing we're going to look at is a very special kind of exponential growth, and this is what we call something doubling. Let's say we had 100 bacteria, and it doubled every hour. At the beginning of the experiment, we have 100. After 1 hour has gone by, how many bacteria do we have? Yep.
200.
200. It's 200, but I want you to think of it as 100 times 2 to the first, okay, to start to see a pattern. How many bacteria would we have after 2 hours? Yep. 400, but I want you to think of it as the original amount times 2 to the second. Now, I don't want to know how many bacteria are in the third hour. Can somebody tell me how you could think of how many bacteria? I want to think of the pattern you see. Yep.
So 100 times 2 to the third.
100 times 2 to the third. And in general, it's 100 times 2 to the t. The reason this is a 2 is because we are dealing with something doubling. Okay? When you double something, that is 100% growth. That's what doubling means. 100% growth. Well, think about what would happen in our formula if you plug in 100% for r. 100% is 1. 1 plus 1, that's why the middle is a 2. Okay? In exponentially double formulas. So it's very similar to the formula we had. It's just you've got to be a little bit careful with the exponent, because when you're dealing with exponential growth and something doubling, this should be the number of doubling cycles. That's what the exponent has to be. It's the number of doubling cycles. So for example, if something doubled every 5 hours and 15 hours had gone by, I would not want to say that it's doubled 15 times. It hasn't. Right? If it doubles every 5 hours and 15 hours have gone by, that's 15 hours of time divided by 5. That means it's doubled 3 times. Okay, so when you're dealing with doubling, make sure your exponent is the number of doubling cycles. And that's how you figure it out. If the cycle length to double is a 1, well, then it doesn't change anything. 15 hours go by, it doubles every hour, it's 15 doubling cycles. Okay. So we're not, I'm not going to graph this one, I just want to set it up. What's the initial amount of bacteria that we have in this problem? Yep, 100. Now, the key here is they don't tell you a growth rate as a percentage. They word it differently. They say the bacteria is doubling. Doubling is really what kind of growth rate? What percentage? Yeah, 100%. That's 100% growth. So if you fill in 1 right there, and then add it to 1, that's how you get the 2. So doubling always should have a 2 in the parentheses. And the exponent is t divided by the length of time to double. What's the length of the time to double in this problem?
1 hour.
Yeah, it's just 1 hour, so it doesn't really change anything. You could just write t. But now you would graph that in y1, You would graph 350,000 in y2, and you'd see where they cross. And the last thing is the opposite of doubling. What's the opposite of doubling? Yep, halving. Okay. And that's called, anybody know what that's called? A special name for it. That's called a half-life. Okay, so half-life is the amount of time it takes for a substance to have half of that substance left. Usually you see half-life when you talk about like nuclear like radiation. So if something had like a half-life of 10,000 years, that means if you produced 1 pound of nuclear waste today, 10,000 years from now, there'll only be half a pound left. And then in another 10,000 years, there'll be a quarter of a pound left. Okay, but it's exactly the same idea as doubling, except you use a 1/2. The reason it's a 1/2 is because halving is a decrease of 50%. That's what half means. You're decreasing it by 50%. And we can look at an example tomorrow, but it's the same idea. You graph it in y1, you graph something else in y2, and you have to see where they cross. So any question on the exponential decay formula for half-life? All right, so those are the questions tonight. It's a lot of individual questions, 4 through 7 and 47 to 49. Those are the only two ranges. I think it's like 16 or 17 questions. So remember, that will be due on Wednesday. Okay, so we'll look at that first thing. And then we'll continue on with 5.4. We skip 5.2 and 5.3. So if you'll notice, we don't do them. I think those two sections are more about like finances, so they just don't fit into pre-cal as well.